Hello, my name is SungWonLee. The topic of my presentation is malicious behavior detection method using API sequence in binary execution path. The contents of the study will be presented in the order of introduction, proposed method, experiments, and discussion conclusions. Before going into the main text, let's start with an introduction. Recently, with the rapid development of network and ICT technologies, the amount of malware has been increasing exponentially. In addition, malware variants that are made by altering existing malware has also been increasing rapidly, and the forms of malware attacks are also becoming quite diverse. In this presentation, a malicious behavior detect method using static analysis-based execution path searches will be proposed first to maximize the efficiency of malicious behavior detection. Although the main analysis method is based on static analysis because it is conducted at the code level, the effect of dynamic analysis can be expected because it tracks the binary execution path to grasp the behavior. In the main text, I will explain in detail the proposed method. Let's look at the architecture and flow of the proposed method. First, the malware executable file is converted into disassembled binary code through the binary reverse engineering tool IDA. The IDA extracts the disassembled code for the executable file, and the relevant file is again used as data for the static execution path search proposed in this presentation. Since malicious behaviors are determined by the API call sequence found the execution path searching, and API extraction process is undergone. The core of the static execution path search in this paper is that the instruction set and subroutines are divided into true and false ones according to the branch instruction before they are searched. First, among the assembled instructions and instructions for branch are JG, JGR, and so on. As for the branch point, comparison instructions such as CMP and tests that occur before the branch instruction are issued are made through logical operation instructions such as SOR. We divide true and false marks according to branch instructions to research all instruction set and subroutines. The IDA disassembled code can identify the instruction set and subroutine used in the search. Instruction sets and subroutine are basic blocks, which are functions that perform some action in the functions are made with a special purpose. The IDA provides the IDA Python, which is a Python script to provide powerful processing activities for binary code. In the code on the left, after CMP instruction in the first line, the binary code local 401460 is branched into the instruction set of local 40148 due to in the JNG in the 8th line, which is a branch instruction. If the result of the comparison is true, the binary code will be branched into local 401488 and it first into local 401484 for to summarize finally. Local 401460 is a binary code which is branched into local 401488. When it is true and into local 401488, when it is false, its binary code is visualized as shown on the right. This mechanism is applied equally even when there are subroutines in the instruction set. If there is a subroutine in the instruction set, like a binary code on the left, the subroutine is entered and the execution path search above is performed. The binary code is visualized as shown on the right. In this study, malicious behavior are detected based on Windows APIs. Applications use API for purpose of using system, resource or interacting with other applications, and APIs are called from the program. Windows applications use Windows API in most cases, and APIs are included in dynamic libraries. Those pieces of malware that are executed based on Windows also use the Windows APIs, and information on the APIs can be used as good information to determine malware behaviors. Malicious behavior will be detected based on the API information discovered during binary execution path searches according to the proposed method. I'll explain it through example code. The corresponding code branch from local 4017884 into local 4185DD when it has been found to be true through the comparison instruction on the 7th line, and local 4185DD branch into local 42899 when it has been found to be true through the comparison instruction. The 50th through the 21st line are same search process on the one shown above, and local 4268DE is defined as a normal mark instead of true or false mark because the subroutine for 88930 is simple code in line 23 without any comparison instruction. The mutual relationship between the instruction set and the subroutine can be visualized as shown on the right. Next, the normal, true, and false mark application mechanism is applied to the APIs called in the line 46, 11, 17, and 26 of the code. The interaction between API and behaviors of the API is visualized as shown in the right figure. After going through several steps, the code on the left is finally visualized as shown in the figure on the right. The previous example was intended for a piece of code. However, it is difficult to express all of them because there are too many APIs for actual samples. When all APIs are used for graph imaging, and analyze time may be too long and the readability may be degraded. In this study, APIs are reclassified into 25 upper categories to make clear judgment and increasing time efficiency. Such a classification not only has many categories to which APIs commonly belong, although they have been already classified in MSDN, but also too abstract to understanding behaviors. For instance, all process-related APIs are included in the category process, but whether the relevant API created, deleted, or accessed process cannot be known. Now, now that the theoretical parts of the proposed method has been explained, I will explain the analysis and result of the sample. In this study, malicious behavior are detected based on the interactions between API using binary static execution path researches. Previous API sequence-based static analysis study had a shortcoming of being unable to accurately understanding malware behavior because they simply list or collected APIs. However, the method proposed in this study enabled to understanding of the interaction between APIs because it used execution path search despite that it is a static analysis, so that the effect of dynamic analysis can be expected. As a representative example, this is a picture analyzed by the proposed method of Trojan malicious binary. The barrier uses APIs such as string, system information, module, and process. In particular, if you analyze the API using the shade red area, you can check it by injecting the code into the remote process calling load library and possible injection and calling load library and possibly injecting the code into a DLA. The existing simple API collection and listening method, the API monitor-based dynamic analysis, and the method proposed are expressed in sequence as follows. The previous sequence listening method can be shown to have API sequence different from those that appear in the dynamic analysis that directly execute API to analyze. However, the API sequence in the method proposed in this paper can be identified to be similar to those appearing in dynamic analysis. As a result of analyzing a number of samples, it was possible to confirm the general graph of 6 malicious behavior: DLL injection, downloader, IAT hooking, keylogger, screen capture, and anti-debugging. Let's talk about efficiency. We show the efficiency of the proposed method compared with previous simple signature information corrections. These are 7 methods of simple listing or correcting code level information such as opcode, engram, bytecode, API, strings, and so on. These are examples applied to be code on the left. The test set is 1236 pieces of randomly generated malware, and all of them include an IAT. Because the method proposed analyzes the interaction between APIs. First, through the identified common behavior graphs, each malicious behavior was analyzed because on the data set consists of 1236 pieces of malwares. Figure shows graph of comparison between the method proposed in this study and the existing detection method. DLL injection, downloader, keylogger, IAT hooking, screen capture, and anti-debugging. It can be seen that the proposed methods show larger numbers of detection of the malicious behaviors, DLL injection, IAT hooking, screen capture, and anti-debugging, when compared to the existing detection method. However, it can be seen that the method proposed in this study show very similar number of detection of other malicious behaviors, such as downloader and keylogger when compared to the existing detection method. This is because the relevant behavior perform API interactions that are too simple to make the relevant behavior to be judged to be malicious. This means that the structure of the sequence is too simple to detect malicious behaviors, which is the reason why the accuracy of detection is lowered. However, it can be seen that the more complex malicious behavior, the higher the detection efficiency. Figure showing detection efficiency according to behavior complexity. The efficiency shown in the graph is the highest efficiency among used studies compared to the proposed method. This means that the more complex the malicious behaviors, the higher the efficiency of detection. Finally, the conclusion. Propose a method to detection execution paths based on static analysis and judgment malicious behavior based on the correlation of APIs. The static analysis method is used, but the advantage of dynamic analysis applied. The more complex and malicious behavior, the higher the efficiency of detection. In the future study, the frequencies of behavior will be added to prepare grounds for judgment of detailed behaviors. Thank you for watching.